Buenas tardes. And first of all, thank you very much for the invitation for us to come here and talk to you about our work. Karim just did that on some of our projects. I'm going to talk about something a little different. But yeah, thank you very much, Damian, Eugenia, and all of the organizers. It's a great pleasure to come here. Unfortunately, we couldn't come for the whole week. Maybe you saw our daughters outside. There are excuses for not coming for the entire time. But in any case, it's really a great pleasure to finally come and talk to people in person. I think it's the first time we have a scientific conference since the pandemic started. And it has been a grueling 2 years stuck at home. So it's very nice to come out and actually being able to talk to people face to face for the first time in quite a while. And it's also a pleasure to be able to talk about my work here. I guess this presentation is going to be a little different maybe from what you have seen so far, in that I am not going to go into a lot of detail in terms of the science. If you have any questions about what I'm going to talk about here scientifically, please come talk to me later today or tomorrow. We're going to be here until the end of the conference now. But my idea here is to present some topics for discussion, show some of the things that I'm working on in terms of instrumentation projects, and open up some topics for discussion, especially for the discussion that we're going to have later on here. But again, if you have any interests, specific interests, I can give you more details and later today or tomorrow. I'm gonna motivate the instrumentation part of the talk on a very biased manner, because I work with extragalactic astrophysics and galaxy formation. So I'm gonna briefly discuss some of the outstanding problems that we have. And the idea here is that we usually talk about galaxy formation in terms of the formation of the large scale structure from the fluctuations in the cosmic microwave background that we can see. For the most part, it works fairly well. I know there's some kinks here and there, but we actually know we can reproduce numerically the formation of large scale structure very well. But when it comes to the formation of stars and the galaxies and the processing of the gas inside those halos, that becomes very difficult, because there are many other physical processes beyond just gravity, like mechanical and radiative feedback, turbulence, magnetic fields, all of those things that we pretend do not exist, so that it becomes simpler. But of course, it can get very complicated when we go into the details, and some people call this the gastrophysics of galaxy formation. But then this is where the details, the devil lies in the details, and that becomes quite complicated. In general, we can have this very classical view of galaxy formation from a dark matter halo. You have hot gas that gradually cools, and it has some kind of angular momentum that generates a disk in there. But it can get a little more complicated, for example, when you think about the evolution of star formation as a function of cosmic time. So as you can see in this review by Maddow and Dickinson from 2014, this has the star formation rate density of the universe has evolved quite a bit, and we have to explain how and why that happened in the last, let's say, 10 billion years, and even before that, why there's a peak in that evolution. Part of the explanation, we do know that at least it lies in the evolution of galaxies themselves. So we know, for example, that the so-called main sequence of galaxies evolves. You have galaxies of the same mass in the past. They were individually forming more stars per unit time than other galaxies of the same mass today. So we do know that galaxies themselves are different in the past. And some of that is related to what we call downsizing, in that a lot of the processes that happen in high mass galaxies have been moving to low mass galaxies. For example, star formation, and the big galaxies were the ones forming stars in the past, and now it's mostly not necessarily low mass, but a lot of the star formation in the local universe happens in the low mass galaxies. And the high mass galaxies, they formed very early and very quickly, and that moved gradually, as we can see in this paper by Thomas, to low mass galaxies. So we do know that galaxy properties have to be evolving as a function of cosmic time. But then again, we cannot, there are a lot of other scaling relations between galaxies that we have to take into account. For example, the mass metallicity relation. We know that also evolved as a function of time. As we can see here in this paper by Maiolino in 2008, the galaxies had lower metallicity in the past, especially the low mass galaxies. So low mass galaxies were a different beast in the past, and they had much fewer metals than they have today. So let's take that with a grain of salt, and that's going to come again later in the talk, in that not all galaxies, especially not the low mass galaxies in the high universe, they're not necessarily dusty metal-rich galaxies. And at the same time, if we think, I like this plot because it's very visually compelling in the sense that how much of the star formation rate density in the universe is located in galaxies of different masses as a function of time, and you can see that this can be more skewed towards higher or lower mass depending on the redshift. But especially when you go to high redshift, observations are very biased towards the high mass galaxies, right? So if you go very deep, depending on how you probe this, of course, this is going to depend a lot on the type of project that you're doing. But just if you take galaxies higher than 10% solar masses, you're only observing half the star formation rate density of the universe at a given time, especially at beyond redshift 1 or 2. So what happens in this and here, it's very difficult to investigate that sort of thing today. And that's where we start to get into the necessity for the next generation telescopes. And here I'm going to be talking more specifically about the 30-meter class that's coming up and other beasts like that. We do know that hopefully there are 3 telescopes coming online in the next decade. The Giant Magellan Telescope in Chile, ESO, the ELT, also in Chile, and the 30-meter telescope, hopefully in Hawaii. We're not sure yet. Hopefully that'll work out well. And especially I'm going to talk a little bit more about the ELT now. I like this picture because they have some trucks and some people here that gives you some scale of the size of that thing. And specifically, I'm going to be talking about Mosaic, which is a project that I'm involved with. This is a multi-object spectrograph that will be built for the ELT. They have a lot of very general science goals, of course, from first galaxies to resolve stellar population beyond the local group, even formation of exoplanets, evolution of large-scale structures. So there's a wide breadth of topics that it's going to tackle, and that's because it's a very versatile instrument. It has many different modes. It has multi-object spectroscopy, and it has IFUs. So it covers all the way from 450, maybe a little bluer. We're working on that, but from 450 nanometers all the way to the end of the H band at 1800. You can do a lot of that at the same time. It's a multi-object, so it uses fibers. It has a lot of fibers that it can deploy at the same time as well. And it also has the IFU, which is going to be done in the near-infrared. And this is also with a multiplex capability, so you can do many IFUs at the same time within the field of view. So this is just a table for you to have an idea, and especially I want to call the attention for the wavelength range here from 0.45 to 1.8 microns. It has both low and high resolution modes, so you can do 4,000 and 18,000 up to you can choose which one you want. And especially the multiplex, this is quite nice. You can do up to 200 objects at a given time with the fibers, and the IFUs, you can do 8, maybe 10 IFUs at a given time. So it's quite, as you can see, you can do a lot of stuff with this instrument. And it's a big team of people working on many aspects of the instrument, even though we're almost 10 years from point and from seeing first light. I'm just zooming in so you can see that I'm actually on the team. And I'm one of the coordinators, along with Mirka Desorzovatsky and Chris Konsulis. We're coordinating one of the science working groups that are studying science cases for the instrument, along with all of the other groups that you can see here. And we're trying to investigate what is the best use of the telescope and how we can design it a little bit better to fit those goals. So just I'm going to give you, this is just to get started, one of the examples that what you can do with the instrument. Some of you may recognize this. This is surface density of star formation rate as a function of surface density of gas. It's known as the Schmidt-Kennicutt relation. This is resolved for local galaxies, and you can see some high redshift galaxies here as well. The idea is that when you use the IFUs in current generation telescopes, you can either do something like this with adaptive optics at high Z, or something like this at high Z without adaptive optics. So, but then you lose a lot of the resolution. The ELT can come down to something like this, and it fits well with, it complements a lot with what's being done with ALMA and what's going to come out of SK. So we're going to be able to probe this relation down to not only the brightest clumps in the galaxies, but we can observe also the surrounding ISM and not just be biased by what we see with the IFU unit. But something that I think relates a lot to a lot of the projects that we have seen today. This is something that I've done a while ago, and this has been published in 2012. At the time, this was the deepest spectroscopic survey of Green Valley galaxies, so I was using CAC. And we had something like almost 10 hours of pointing per mask with the 10-meter telescope. And this was pretty much the best that we could do at the time. And you can see the absorption lines here on a 24th magnitude galaxy. And I think this is state of the art of what we could do at the time. This is important because, and I'm not going to go into the details of how this is calculated. If you want, you can ask me later. But we managed to see how quenching happened in Green Valley galaxies when we went to high Z. This was fast. This was happening especially for the more luminous galaxies, presenting another aspect, let's say, of downsizing in galaxy evolution. More recently, this is a paper that we have just published. It came out this year. It was accepted last year. We did a similar kind of study. Now we have this SFA measurement, which is, you can think of as a time derivative of the star formation rate of a galaxy. It works very well, but you do need the same region here. You do need to see H alpha and absorption, that kind of thing. But we managed to separate that into morphologies using some deep learning that we had, and we see that Green Valley ellipticals quench faster than the Green Valley disk galaxies, and it goes all the way. That difference goes all the way into the blue cloud, and not only the Green Valley. This was part of what Karim mentioned in her talk. This is something that it's very interesting because the elliptical galaxies, this is the SFA, which you can think of this time derivative. Very red means strong quenching, very blue means strong bursting. So you can also measure positive derivatives in that sense. The ellipticals all clump around here because they're all very, this is as a function of asymmetry as well, and they're all very symmetric in general. But especially when you go to the spiral galaxies, if you divide them in terms of asymmetry, you can see that the more symmetric spirals are typically quenching. They're redder in this scale here. But the more asymmetric spirals are actually bursting, which means that this is probably happening during some sort of merging, either minor or major merging. They're increasing their star formation rates at that distance. So this is going, and that depends very strongly on asymmetry. So we have this very general schematic here of how we picture a galaxy evolution to happen across. This is a function of color. Usually the asymmetric galaxies have some sort of bursting here. And especially this slow track or fast track depends a lot on the morphologies, which is reasonable when you think about it, because The secular evolution happens in a slow track if you don't have any major mergers or any strong events, any dramatic events happening with the galaxy. They're gonna slowly evolve through the Green Valley to the right sequence. But if they have some sort of merger that actually changes their morphologies, they will move through the Green Valley faster, because that accelerates the process of using or maybe expelling the gas from the galaxy. The interesting thing here is that when we move to high redshift, and this is an example of what we can do with Mosaic, we move that 4,000 angstrom break, which is one of the main indices that you can use for galaxy evolution. When you move that to high redshift, you go into the J and H band, so we can probe that sort of thing on redshifts around 2 and 3 when the peak of star formation was happening in the universe. So you can do some very interesting science, not only staying here as we have done thus far, but you can actually do this type of study at higher redshifts. Thus far, it has been really difficult to do anything like that. I love this project. I think it was ahead of its time, let's say, in the sense that they were really trying to go down and probe the stellar populations of galaxies down to 10 solar masses, which was quite a challenge, being complete down to Z of 1-ish. But they required, at that time, 20 hours per pointing with the VLT. So it was a very time-consuming project. So it was a big challenge. But now we might be able to do something like stellar mass of 10 to the 8th at Z of 2 with Mosaic, just because, of course, we're using a 40-meter telescope. We can do a lot better than we can possibly do today. Again, some numbers for you. The ELT Mosaic will push this limit up to J or H up to 27. So you can think of doing absorption lines of 27 magnitude galaxies. And this is quite fainter than L star. So we're not going to be limited to the brightest galaxies anymore. So not only can we go to higher redshift, but we can actually do it for smaller galaxies down to smaller masses. Of course, that depends on the amount of time that you're going to spend on each one, but it's actually doable. So this can really push our understanding forward of galaxy formation at high Z. I'm going to switch gears a little bit here and talk about submillimeter galaxies, submillimeter sky. This is a project for the Gran Telescopio Milimétrico, the large millimeter telescope in Mexico. Our Mexican colleagues, I'm sure they're familiar with this. This is a 50-meter telescope, 50-meter antenna in Mexico. This house here gives you an idea of scale for this thing. It's a very big antenna. And the submillimeter sky is quite interesting when you think about redshift. I like this animation by Caitlin Casey to show what I mean here. This is going to show an SED of a galaxy as a function of redshift. And of course, as you go to higher redshift, you can see the peak of the emission is going down. But if you're going redward of the peak here, and this is dust emission in galaxies, if you go to, if you stay redward of this, at the same time that you have this going down, it actually have this going red. It's going to the right, of course, because the redshift is moving the SED to redder wavelengths. And this compensates a little bit. So the flux that you observe at a given wavelength of approximately, let's say, 1 millimeter is constant, or it might even increase a little bit. So it's what we call the negative K correction. It's very interesting because then it makes it easier to observe galaxies at higher redshift. Another way of seeing this is this is already 20 years old by now, but it gives you an idea that if you're doing the optical or very blue bands, of course the flux goes down as you go to higher redshift. But if you have those bands here that are redward of the peak, then you can even have an increase in flux for the same galaxy if you just put it further away. Just because you're moving the peak into your observing band, you have the fixed observing band. And this negative K correction allows you to see galaxies to very high redshift, and it becomes an advantage when you're trying to see that sort of thing. And at the same time, Toltec specifically is this instrument that's going to use kinetic inductance detectors. It's a very modern technology. It's very interesting. And they're going to be able to observe all of the three bands, which are 1.1, 1.4, and 2 millimeters simultaneously. So you can see a lot of the high redshift universe in a very efficient manner, especially if you have this is 7,000, sorry, this is a typo, not 70. But you have 7,000 detectors, and it becomes very efficient to map. It's still just one antenna. You don't have the interferometric capabilities of ALMA, for example, but you can map the sky very quickly and very efficiently. So depending on the band that you're using, you can do, this is the maximum speed prediction. It might be a little lower than that, but you can safely say that you're going to be able to do something like 10 square degrees by square megajansky per hour. And just for comparison, the state of the art nowadays is something like 0.07. This is one of the most advanced submillimeter surveys that we have so far. So we expect an increase in mapping efficiency of by a factor of 100 or so. So this is going to be great to see the high redshift. And usually when we think about submillimeter galaxies, you're very biased again towards that very massive and those giant things that are forming 1,000 stars per year. But now we can see the more normal galaxies to very high redshift. So for example, we're thinking about two main surveys. This is what the PIs of the projects have designed thus far. So this is one circuit that's going to go down to 0.25 millijansky per beam and probe around 100 square degrees in the sky. So it's a very ambitious project, much greater than anything that we have today. And it's going to be excellent, for example, to probe for protoclusters at very high redshift, the formation of the first structures, not necessarily clusters formed, but just those protoclusters. Usually they're very well probed by the submillimeter galaxies. At the same time, they also have another project, another 100-hour project or so, which is the 1 square degree ultra deep galaxy survey. This is much smaller, of course, but then again, you're going down to 0.025 millijansky per. So you're going very deep. This is around the diffusion limit of the instrument. And again, if you compare with Scuba 2, which is limited to approximately millijansky or so in the continuum, you can see that we're going to go much deeper, and we're going to be able to see not just the brightest galaxies in the early universe, but the normal star-forming galaxies. And this is just to give you an idea of something that we're working on. This is a very quick and dirty prediction that I've been doing with a student as a detection limits as a function of stellar mass and redshift. And according to this, we can see pretty much all the galaxies around above 10 to the 10 solar masses and out to redshifts 5 or 6, I don't know. But of course, first of all, this is very preliminary. This is not definite yet. But especially, this is very dependent on the metal contents of the galaxy. So it's going to be interesting to see how those predictions change, and especially once the data starts to come in, how that's going to change for the galaxies. Remember that we don't know exactly the metal content of especially the low mass galaxies at high redshift, and we're looking at the dust continuum. So that's very, very dependent on the metal content of the galaxy, right? So this can change by quite a bit, and it's going to be interesting to see. But at least we're going to be able to probe for that sort of thing in a statistical manner with Toltec. So it's a very exciting prospect. And for the final part of my talk, I'm going to allow myself to be maybe a little political here, but I think it's something that we need to discuss, and I think it fits very well with the topic of this conference in terms of trying to foment collaboration and cooperation between people, especially here in Latin America. I'm using this as an example of different ways, let's say, of doing things. For example, Brazil, and not Brazil, this is the state of São Paulo agency. They're investing on the GMT, which is one of the next generation telescopes. But this is going to be for 4% of observing time for the São Paulo astronomers, which on one hand, it can be really interesting because it guarantees time for those researchers in São Paulo. On the other hand, it limits the amount, the type of science that you can do because you cannot take a lot of time on telescope. It's going to be 4% divided between everyone, and you may well know that the state of São Paulo is pretty big and has a lot of people working. When you compare that, for example, with the guaranteed time observing for MOSAIC, and again, this is going to be divided between the surveys, but it's a minimum of 125 nights guaranteed time for the ELT. So when you think about that, of course, I'm not saying that this is bad. I'm just saying that you cannot rely only on that to have high impact science because you're going to be biased towards smaller projects divided between smaller groups. When you do something like that, you can pretty much guarantee that you're going to have a paper that everyone's going to cite. So this is the type of project that at least some of the science in a given country should be aiming for, and not restricting ourselves for something like that. I think every Argentinian here is it's pretty much the same with Gemini and Brazilian time in Gemini. We're restricted to projects that are few hours, always less than 10 hours per project. So we do know that this limits the kind of science that you can do in the long run. And when you think about that, you also have to think about money. So I'm just using NSF as an example here, and NSF averages 130,000 per project approved, and it's one of the main financiers of science in the US. But when we use the example of the Brazilian agency, especially in 2020, it had $3 million, sorry, this is $3 million, not guys. But it had $3 million for absolutely everyone in the country that had to be divided amongst everyone. It was an 87% drop with respect to 2019. So you can think that if you have to divide $3 million between a whole country, and Brazil is a pretty big country, I have to say, every individual project has been awarded, I think, like $2,000 on average, I'd say. So it's very hard to do some sort of ambitious science when you're dividing like all of that money into tiny bits like that. And again, if you compare that with something like JWST, of course, it's an international collaboration. It's not just NASA, but you're thinking about a project that costs $10 billion. And whereas instrumentation projects in Brazil, the Sirius accelerator, it had some difficulty getting completed. And if you think about the ESO, many of you must have heard about the ESO thing in Brazil, and it was this whole ordeal. In the end, we have been suspended from the project. And this, of course, we do have, and from what I've heard just today, I think my Argentinian colleagues are going to agree that we do have a problem with financing in science. We certainly do in Brazil, I have to say. But if we're all competing for projects in terms of $2,000 each, then we're never going to really amount to anything. We do have to collaborate in some sense, and especially I hope I have convinced you with the MOSAIC and Tiltec examples that those projects, they have a lot of investment going in, but at the same time the outcome is very positive. They're really coming up with something that's going to have a high impact. We do have some projects that I think are worthy of mention. For example, S+, some of you may know, so I know some of you are involved with this. This is a project that is led by Cláudia Mendes de Oliveira in São Paulo. It's not a big telescope, it's an 80 centimeter telescope, but it's doing a large survey of the sky and the optical. It's got some interesting results. It's not super deep, but it has a lot of people working in it, and it has a lot of science outcome coming out of it. And as an example, this is something that we have just had approved in Rio. I'm the PI of the project, but Karim, Martin, who's also here, and John Andrade are part of the project. We got something like $100,000 for this. And the idea is to create this network for astronomical instrumentation And it has some different projects going on, Mosaic, Toltec, maybe the construction of a skipper, CCD, we're going to work towards that. Gianna works a lot on astrochemical studies, and she does a lot of studies in the laboratory, which is quite interesting, but she also needs a lot of investment because that's actually hardware that she needs to build and to maintain in order to do her research. It was an interesting project to write, an interesting proposal to write, because it was very difficult. I don't think it was the greatest text I've ever written, because it was this, I was always joking with my collaborators in that it was this Frankenstein of a project that I had to cut pieces here and there and put it all together. But at the same time, I think this sort of strategy is important. And this is, I think, the main point that I'm trying to raise here, that we need to collaborate and we need to create these networks, not only to have maybe higher funding for individual projects and maybe thinking a little bigger, but especially because we also need, and this is something I've written here, we need to train the younger generation of astronomers and the younger generation of scientists in using, in having access to this type of resources and joining this type of project, because we need to develop the expertise also in our community so that we're not always dependent on that 4% or that 3% of telescope time to do more restrictive science sometimes, but we also need to invest in people that have the expertise of joining a bigger project and maybe developing that when the tides are higher, let's say, and we have some governments that might be able to fund science a little bit more. Certainly not the case in Brazil right now. But when that time comes, we actually have the expertise to develop some more ambitious instrumentation projects in the country that have the potential for higher impact. So just to put up my conclusions here, Mosaic, this is going to be the workhorse instrument for the LT. I think it is a little bit of a jack of all trades. It's not doing anything revolutionary in terms of its design, but it's doing all of it really well. And you're going to have access to 200 fibers at a time, or maybe 8 to 10 IFU units in a 40-meter telescope. So that's going to be amazing. Toltec, it's going to be great for mapping the sky. Doesn't have, of course, the sensitivity of ALMA, let's say, but it's going to do a much larger part of the sky. It's much more efficient to map the sky, and then maybe you can use ALMA for follow-up. But if you want to do a map of the sky in the sub-millimeter, Toltec is going to be an amazing machine. And that's my talking point here. We can think about all of those ideas in terms of opportunities to collaborate and think strategically in terms of where we want to be in 10 years, let's say. So when it comes to Mosaic or Toltec, for example, I cannot guarantee that you are going to be able to join because I'm not the PI in those projects. But I can certainly try to do something. I think it's a great opportunity if you want to do something in that sense. And I know there are options to join. There are some ways that you can apply to join those projects. It's not up to me personally, but you can do something like that. But when it comes to that network that thus far is just a state collaboration within our small group of people, then I'm the boss there and I can do whatever I want. So I'm very open to collaborations, and I'm certainly very open to talking to you. And I hope I've tickled your mind in a way that you might be interested at least in discussing all those things with me. So thank you very much for your attention, and I hope to hear your questions.
Thank you, Thiago. We will keep talking about this in the roundtable questions.
I have questions with Toltec. So in this lumped element, I think the spatial resolution, and also you get some kind of spectral resolution, right? Because with these kits, you measure also the frequency of the photon with some uncertainty. Do you know what would be kind of a spectral resolution?
There's no spectral resolution because this this is not interferometric, or it's not heterodyne receivers. So you don't have a spectrum. It's continuum. So you have a band. Sorry, let me try to put this up. So you don't have a spectral resolution because you're doing just continuum in that sense. So it's much faster this way, but you don't have the spectral information, at least not with this. If you want the spectrum, you should. There are other receivers in the LNT, or you can do it with ALMA if it's too faint, but no spectral resolution. It's just continuum. But in terms of the resolution, you can think about the beam size here. 5 arc seconds for the 1 millimeter band and 10 arc seconds for this. I forgot to say, but this is diffraction limited in the submillimeter. So this depends a lot on the size of your antenna. And this is another advantage here because your beam size is much smaller, your confusion limit is much fainter. Because if you have this beam like this big, you're going to start confusing much earlier. So that's another reason why you can go down to 0.025 millijanskis for the sources.
Can I keep asking? Can I continue asking? Since I have a microphone.
I think there's.
So, looking at the submillimeter has been very effective to find the strong lenses because it gets very magnified sources. Did someone estimate how many of these strong lenses you could find in the survey?
I'm sure there's someone working with that. I know they have mentioned that, but I don't know the numbers off the top of my head.
Oh, okay. So let's talk.
Do you have those numbers? Yes. So.
And just a comment that maybe we can discuss during the roundtable. But the problem that you mentioned in Brazil, that we are well aware that the total amount of money is short, and it's both gets spread a lot of small grants. Then in Argentina, this is even more. I mean, there is even less money, and it gets totally spread. So we have the very same problem. So maybe we can discuss this in the roundtable.
And I think I have a question back there. Yes, certainly we can discuss that.
I was just wondering, with Mosaic, what's the rationale for not going to further into the near-infrared KS band?
We wanted to, but there's some limitations to what you can do in terms of space and money. So you do have to make some sacrifice at some point. It's not that we don't want to, but the K-band has been already discarded at this point because we had to choose what to invest in terms of what bands to observe and what would actually fit in the chamber so that we can do all of that at the same time. So I think it was one of the hardest sacrifices that were made in the early stages of the project.
Question? Online, do you have some questions? No? Mosaic, you mentioned, it's the field of view is the IFU.
So this up here. So the field of view of an individual unit of the IFU is 2.5 arc seconds with AO. But all of that, you can deploy multiple IFUs within the field of view. Forgot the exact number. I think it's something like 6 arc minutes. I'd have to check, but the whole thing is about, I think it's 6 arc minutes.
How many IFU units are?
Guaranteed 8. I think they're trying to go for 10.
And you have some kind of super IFU joining all the together, something like that, or?
Not that I know of. You might be able to have to think of how to join everything. Maybe there would be a gap in that. That's a good. I don't think there's any plan to do that. Maybe even do some sort of mosaicing to fill in the gaps, but I don't know the details.